I will be talking about advances in superconductor VLSI and how they can enable next generation of high performance computing. I'll begin by outlining the key challenges in scaling superconductor electronics and discuss our efforts at the Sport Lab at USC to address them. Well, this work spanned multiple projects, collaboration between groups across several institutions in US, and I will mostly focus on our contribution and results from a sport lab. And by the end of the talk, I hope to convince you that superconductor electronic is not just a promising alternative or a gimmick, but a realistic, viable technology that for the post-CMOS or going beyond CMOS computing. Okay, so let's go next slide. This is our picture of our university, USC, and this is a picture of our group with three of the recent graduates from the Sport Lab. And the SPORT stands for System Power Optimization and Regulation Technology. And the focus of the laboratory is basically reducing the power in computation, most likely, and increase efficiency. So this, the outline of my talk, as I mentioned, I will go very briefly over some of the superconductor basics. So in this talk series of the seminars, we talk a lot about superconductors and basics of it, so I don't focus on it. I just mentioned that what is superconductor? It's defined by three properties. One is the zero resistivity. Second is the Meissner effect, which is perfect diamagnetism. Third one I didn't show here is the thermodynamic effect, but we are mostly focused in the electronic part in the two parts, which is zero resistivity and Meissner effect. One property of the superconductor is if you have a superconductor loop, when the magnetic field tries to penetrate this loop, it will penetrate it in a quantized way due to a screening current and existence of Cooper pairs and the quantum properties that bring these Cooper pairs or quasi-boson bring with them. So, of course, you can please go through other seminar talks for the more details and better explanation on the superconductor properties and basics. So these are the applications in the electronic part, not in the magnetic or large scale part. For the superconductor electronics, one of the main applications that currently is commercialized are sensors and detectors like SNSPDs, IR detectors, and magnetic detectors like SQUIDs. And the second application that comes with the microwave properties or optical resistance properties due to quasi-bosons in the impedance on the superconductors is the microwave devices like very sharp filters, good antennas, analog digital converter, resonators, and so on that are used in also quantum computing, radio astronomy, telecommunication, and such. Then the main application that for our group, main application that we will be focusing on is more on the computing part, which includes in sensor computing. So you can implement your sensors and your computing units in a single chip on superconductor cryogenic without adding much of the digital noise that comes usually from the other digital circuits. Signal processing, I will show a small example of FFT and the synthesizing of the FFT which is fast Fourier transform in superconductors. And the other application we are focusing on is improving supercomputing with superconductor VLSI. Quantum computing and encryption are also other applications that we at the Sport Lab are interested in. We had some projects on the fully homomorphic encryptions, and we are trying to do some proposal or work on quantum computing. So this is the switching powers for the superconductor elements and compared to the CMOS. So for the traditional CMOS, this is a 40 nano or 12 nano global foundry process. It's around 10 to the power of 6. This is the Shannon-Newman energy consumption for bit loss and the theoretical limit basically for the logic when you lose a bit or for switching. And in CMOS, it's around at 6 gigahertz, 77 Kelvin. It's around 10 to the power of 6 times this limit. For RSFQ, which is one of the most prominent superconductor technologies and probably the most mature one currently, is 10 to the power of 3. And for the AQFP, which is a reversible computing adiabatic quantum flux parametron, it is at that limit, at the theoretical limit, at 5 gigahertz. And this is a table that compares the switching powers calculated for the arithmetic logic unit. So the main element for us is Josephson junctions. Josephson junction is two superconductors separated with an insulator. And this is the standard sign we will use for showing the Josephson junction from now on. And you can solve the equations, basically Schrödinger equations coupled Schrödinger equation for these two superconductors. That results in two equations. One, we call it current phase relation or DC Josephson effect, which means that you have a current without existing any voltage. There is a constant current in Josephson junction based on the phase shift. And the second equation, which is the AC Josephson effect or voltage phase relation, says that if there is a voltage, there is an oscillation or Josephson junctions, and this is the value of the oscillation. And of course, phi 0 is quantum of flux, which is h over 2e. So the Josephson junction acts as a pendulum, which means that if you go 2 pi around this pendulum, it goes to the initial state without keeping any memory of that. We call this switching. And this is when Josephson junction switch creates a single flux quantum, which is a pulse with the value of phi 0 or the energy of phi 0. And for niobium junctions, which we are using with MIT process, it's around 1 millivolt high and 2 picosecond thickness. And one property that I will show in this talk I'm interested in is the inductance of the Josephson junction. So if you see this equation and solve it for the phi and the phase of it, you will see that there is a inductance in the junction, or there is a inductance-like property in the junction that comes from the current of the junction, which means that you now have an inductance that is related to the current, and you can control that value with the current through the junctions. Now, if you put two junctions together, we call this a superconductor quantum interference device or SQUID. For the SQUID, you can control this value of the inductance with the phase or with the flux that you put inside this loop. So now you have a parametric inductance that can be controlled by external flux or for the junction current. Now, the superconductor logic or RSFQ is one of the main logic that we are using. As I said, it's one of the most mature processes. I will not go through how this logic works or what is the property of it. For that, please go and see the talk from Dr. Holmes, which is also available on our website and our YouTube, which titles How It Works, Single Flux Quantum Logic. And I'm just mentioning what is the benefits of the RSFQ, which is low switching energy, as we showed, is around 10 to the power of minus 19 joule. Ultra high speed around 50 gigahertz. And also one other aspect of superconductor logic or circuits that may be overlooked is the interconnects. In CMOS, your interconnect delay depends on RC value, and it increases quadratically with the length of the interconnects or the resistor of it. So you need to put a lot of buffer, cut these interconnects, and to manage the delay. And as the CMOS technology becomes smaller and smaller, now the main delay in the circuits are not from the gates, but it's from the interconnects. And that is the main limitation in the speed and also basically VLSI in the CMOS. But in superconductors, this value increases linearly since you don't have a classical resistance. You have an impedance which comes from the Matisse-Bardeen's equations, surface impedance, and that surface impedance doesn't show any real part unless you go to very, very high frequencies. But at the frequencies that our digital circuits works, we can assume that this interconnect delay is 1/3 of the speed of light, or which comes from the 1 over square root of LC, and this value grows linearly. So that is a very big plus in our circuits. But there are, of course, challenges for these circuits. They are deeply pipelined, so all gates need to be clogged. Fan-in, fan-out are one. So if you want to connect one circuit or one gate to multiple gates, you need to put a splitter tree. And a splitter cell is also a RSFQ cell that's almost as big as a gate. So for getting the fan-out of 32, you need to put 1 to 2 or basically 5 level of a splitter tree, or if you have, I don't know, higher splitter numbers, less, but that's a lot of overhead. And in RSFQ circuits, as it gets bigger, that will be the main concern for us. And DC bias is another issue. So the VLSI of the circuits are not as limited by their size, but by their bias, which means that, okay, our circuits are superconductor. It doesn't really consume any bias or any current, but you need to bring this current on the chip anyway. And you need to distribute this current between the gates. If you use resistive distribution network like RSFQ, then those are static power consumptions. If you use eRSFQ and you say, okay, I don't have a distribution network, resistive network, then still you need to bring all this current with the interconnects from the room temperature to your chip. And this current gets very, very big, very fast. And of course, lack of integration density, which I will show for the MIT process, the size of these circuits are big. So for the MIT process that we are using, you can see this document for more details on the process. It's a 9-layer process, have 5 interconnects for the routings, and it's based on niobium material, and 3 niobium layers for the Josephson junctions. And we have the gold-plated contacts. So this is the process we are using currently for fabricating our chips. The issue with this is that the JJ size itself is around 1 micrometer square. And if you include the shunts and the vias needed for making a Josephson junction to switch, it would become 5 micrometer square, which is not a small value if you are familiar with also the CMOS processes that are around 2 nanometer or 4 nanometer processes. So where these limits come from is that the niobium material is a rough material. Second issue with niobium is you cannot process them at high temperature because they get poisoned with oxides. So you cannot really sputter niobium if you have oxygen in your system over 200 degrees Celsius. That results in lower quality of your dielectric. This is the one example of the OR gate that we have designed in our sport lib, and you see the size is around 50 micro by 50 micro for the MIT process. This is simulation results, and we have the measurement results of the OR gate. In the measurements, of course, we need conversion cells, which we call it SFQ to DC converter, and those conversion cells will flip when there is a pulse. So each of these flips or each side's transitions show existence of one pulse. And we can measure with the CMOS like that or connect to CMOS like that. For showing that how useful or how big this technology is, the cells and the current fabrication process, this is an example of arithmetic logic unit. Of course, this is not designed in MIT. It was designed in the STP2 gravity process, which is now called QFAB. And for this, in this process, which it's not as refined as current MIT process, but at the time it was good enough. And what we see is that for the 4-bit arithmetic logic unit, we need a 5 by 5 millimeter area of the chip and around 1 amperes of the bias current to bring to the chip. It was, of course, working at 2.4 milliwatt at 25 gigahertz. And you see that you get a high latency due to the size of the circuit, not the speed of the gates or switching. So we can now classify all these challenges in 3 main categories: in the architecture level, circuit level, device level, and of course we have failure modes like flux trap and noise crosstalk that I will not go through them in this talk. So the architecture level comes from of course, you don't have a standardized EDA tools and cell library. So each group or each basically team that works on these circuits have their own cell library, have their own internal tools. So we try to standardize this by introducing the EDA tool suite, which we call it QPalace. It was first founded by IARPA project called Flux Super Tools. And in this project, we design a suite of tools that goes from the RTL level to chip level. And after that, the project finished in 23, but after that, we continued developing these tools much more and make it basically more user-friendly and more superconductor friendly. And now we can generate directly a GDS that is ready to fabricate from the RTL. And this is the cell library. We call it a SportLib, which is a standard cell library that uses this suite of tools. And we of course test all these cell libraries after fabrications. And this is a fabricated multiplier cell, which the connections are not with PTL, but these are connected with the JTL, which is the Josephson transmission line. And we test this at our cryogenic facility and see the margins and validated the chips. For the other issue is the pass balancing in the architecture level. What does it mean? It means that if you have several levels of circuits, to avoid getting the race condition and getting the signals at the correct pulse frame, you need to provide a full pass balance or be sure that these signals arrive at the correct level at the correct clock frame, which this results in an insertion of a lot of D flip-flop or buffer cells inside your circuit. And if you have the H3 structure or zero skew clocking, your main concern or the main cells would not be the gates, but these DFFs and these splitters. So we try to combine this method, zero skew clocking, with concurrent clocking or clock follow data. In this method, the clock propagates the data, so we pass balance with the delay cells or the gems similar to JTLs or delay lines. And this way, we will not need this many DFFs and a clock distribution tree. We basically have a clock line that just goes through the circuit and propagates the data through it. But of course, in a long, big circuits, this is not, you cannot do all the pass balancing by this concurrent clocking, and you need to break it into parts due to existence of jitter and skew. So you should use a combination, of course. And for the clockings, we have the H3 clocking, we have concurrent clocking or the clock follow data. And IMEC also introduced this method, which is a zero skew clocking by Strong. And in this clocking, they just use the resonance property of the lines. So the clock arrives at all the points at the same time. So the other issue was place and route in the architecture level. For the place and route, we proposed JTL and PTL routing, which we can address this issue and reduce basically the congestion in your circuit. And you make macro cells with JTL routing, doing concurrent clocking inside them, then do PTL routing outside of it. And this is an example of this cell, which is this method of the design, which we design a spiking neural network, works at 10 gigahertz at 2.15 milliwatt power, which is mostly just a static power due to the bias distribution. And the dynamic energy consumption per inference for it is 6.55 femtojoule. It's for the MNIST dataset. And these are the PTL routers, and these are supercells, which are our neurons, and it is concurrent clocked inside. And this is the chip we have fabricated and plan to test in a near future. So then the bias distribution is one other issue. As we said, that if you have DC bias, you need have a very big circuit, with very big amount of bias you need to bring into your circuit. It's around 350 amps for around 10 million junctions, which is not a practical thing to do. So for that, you need to use AC clocking. And in the AC clocking that we propose based on the Semenov's and Tolpigo's paper, we use these cells, these converter cells, and that converts the AC to SFQ pulse and provide the SFQ pulse to the circuit as needed. And we can connect multiple of these cells together and use it as AC biasing. So another issue was the VLSI, or the size of the circuits that we cannot fit on a single chip. So for the expedition project, we say, okay, let's break these circuits into multiple parts and put it on multiple chips and use a SMCM, or the superconductor multi-chip module. This is designed, this part of the integration, by Auburn University, and these chips were designed at USC for integration between multiple groups, of course, here. And interface circuits was designed in the Rochester University. And this is the sample of the Mac chip for the convolutional neural network, basically using for their convolution levels. So again, this was not enough, since as you know, we were using MIT Lincoln lab process, and there the size of the junctions, the inductances, bulk inductances, and the routing really limited us. And with all the proposed architectural improvements, we couldn't really get to the level that make it really compatible for the large scale integration or very large scale VLSI. So we call this sVLSI or superconductor VLSI. And for that, we need to introduce new types of logic, new types of circuits, and new types of applications or devices for the new fabrication process. This is mostly covered under FSTL project, which is a cold phase project supported by ARL. And in this project, we try to reduce the size of the circuits, reduce the power needed for these circuits, and increase the computational density of the circuit. And using for that, we introduce fast phase logic technology. The fast phase logic technology is based on the zero pi junctions, and it is using these odd loop and even pi loops. So what is the pi junction? Pi junction is a Josephson junction with a magnetic layer inside it that results in a phase shift of the value of pi in the junction. So if you have a squeeze loop with pi junction in it or pi phase shift, what happens is this loop needs to go to either 0 or 2 pi value. So there will be a constant current flowing through this loop. And that would result in an interesting things. One is that it will reduce the power you need or the bias you need to put on these loops to basically try to switch them because you already have a current flowing through them from these pi junctions. And second property is you don't really need that much energy to switch the junctions here. Now, if you have an even loop and odd loop connected together, this will act as a biostable element or a kind of like a 2-phi junction, which means that it can be switched just not by phi 0, but by half a phi and half phi 0 or half a flux. So it kind of become half flux quantum. But our fast phase logic is not really just a half flux quantum. So the storage loop switching or this even odd loop switches with the half flux, but the propagation is full pi or a full flux. This is a sample of the DFF cell. As you see, its sizes, if you compare it with SFQ, which was 30 by 30 micrometer, this is now 1.8 by 1.8 micrometer. But for that, we need to fabricate these pi junctions. And this is a comparison we did with compared to the CMOS. And FPL, this is the stack junction and RSFQ technology. As you see, the RSFQ technology is around 4 order of magnitude in size bigger than CMOS. And the area of FPL is 1 or 1.5 order of magnitude bigger just than their CMOS counterpart for the sample 12 nano process. But the power consumption is around 250x, around 2.5 order of magnitude smaller. And this is with the consideration of the cooling power in this. So we added around 300x for the cooling power here to compare these two together. And this is the process stack we propose in this project to be able to implement these pi junctions. We have need the stack of 0 and pi. This would be our switch, the stack of 0 and pi. So we don't really want to switch the pi junction themselves, but the 0 junction that is stacked under the pi junction. So since you are not switching the pi's and you are not switching these stacks that act as your inductances, you really don't need to control them or control their JC that much, but the zero junctions that are switched, you need to have a very good control on it. For this stack, we try to use niobium titanium nitride material. Why? As you remember, I said that the niobium has this problem with being rough and also not be able to process it in the existence of oxide over 200 degrees. So you will have a bad dielectrics. With niobium titanium nitride, you can process them at 420 degrees Celsius, which is similar to the CMOS process. So you can have a very good dielectric properties and use the CMOS process to build this stack. And we try to use for the barriers of the pi junctions ferrimagnetic material, not ferromaterial, so we don't create magnetic flux inside the circuit that results to also issue for the zero junctions. And of course, the stack of the junctions, as you remember, we mentioned that Josephson junction has an inductance on its own, which is related to its current. So if you stack a few junctions, you don't need to put inductances inside your circuit. You can just replace them with this stack. And this part of the fabrication is led by Professor Pedram and Kapadia at USC part and Dr. Holmes, who is doing this fabrication at University of Maryland. We have this test facility at USC for calibration and testing these devices. We have a cryo-cooler from Hypress, their ICT system with 40 RF lines and also the temperature SRS temperature controller system. And in this lab, we are using this system for characterizing the films and also testing our SF2 circuits. This is a pattern that the film and pattern that was fabricated and patterned at the USC 5x5 millimeter chips, and which was patterned like this to put in this our high press probe. And we measure the critical temperature at 12.5 K, which we try to increase it to around 40 K, but currently it is at 12.5, but it's good enough for making digital electronics. And this is the critical current measurement for the 5 micrometer line here. These are the measurement results for our multipliers design, a 2-bit multiplier with the MIT process that we measured in this lab and confirmed this operation. Okay. So one of the other issues in the superconductor and that limits the VLSI is lack of memory. So any questions until this part? Okay. So I just continue then. So we have a lack of memory in superconductor circuits, and we don't have a good solution for that. Using DFFs doesn't really give you the random access part, and using NDROs or non-destructive tests makes it really bulky and control very hard. This is a table that compares different superconductor technologies and memories in different technologies. So you have mostly shift register memories. There are some proposed RAM memories, but the size is not really suitable for using in VLSI. And so we propose this new type of memory, which we call it bistable vortex memory or BVM. And as you see in a even MIT Lincoln Lab 100 microampere per micrometer square, this is basically the smallest memory possible. Other than if you have nanowires, but nanowire technology is not really suitable for the fabrication in classical fabrication process. This is a sample of RSFQ chip memory. We try to make a memory unit with all the controller, readout, and other parts, and we just can fit 128 bits into bank of the memory inside the 5 by 5 millimeter chip, which is not really good. With the FPL cells instead of RSFQ, you can fit around 64 kilobit of memory in the same area. But for the CMOS, this value is around 400 megabit. So we have a long way to go. Therefore, we propose this bistable vortex memory, or BVM, which works with two superconductor loops. One is the storage, the other one is the readout. The good thing about this is it's non-volatile, which means that once you read it, you really don't need to provide bias or feedback or anything to keep the values, and you can read it as many times as you want. And it's very similar to the RAM structure. You have a word line, bit line, and you can just array them together, connect all these cells together without needing any other overhead. And also, they don't really need bias to drive and to read. You just need to provide the correct signals for the write, like this, write 1, write 0, and just send signal for reading the data out. The other part that we had in mind in designing this memory was that we don't want to use any transformers, because first, transformers are bulky, and second thing, it's not compatible to convert this to the FPL technology. So with this structure, we can replace all the inductors with, again, stack junctions and make this really, really compact and small, and just with this stack junction, we can just array them and make a very high density memory compared to, of course, other superconductor technologies. This is an example of 32 by 32 bit array of this memory that we simulated with in JOSIM, and this is the write and read results of the simulation output. And this is some of the circuits that we designed and fabricated and plan to test when the chip arrives, we plan to test these circuits. One other solution for the memory issue in superconductor is using a hybrid superconductor CMOS structure. And Yoshikawa Sensei's group in Japan, Yokohama, showed that they can put 8-bit array, 8 transistor SRAMs, and connect them to the superconductor circuits with the quasi-band junction squeeze or QoS circuits used as sense amplifiers. And with this method, they had 1.2 gigabits per second per channel, and they had, I think, 16 channels or 12 channels from their paper. So we say, okay, we try to also use 8-bit SRAMs and use Josephson junction method as a sense amplifier, and see what is the density that we can get with this memory and what's the speed we can get. I also did some work before on the BiCMOS silicon germanium process when we were at Top University, and in this work we show it in this paper, and we integrated on a SFQ chip. This is also a SFQ chip, which is fabricated with gravity, and this is the CMOS chip we had, or Hsieh chip we had with IHP process. So if we integrate this CMOS with the SFQ, we can use again the flip chip bond methods and 3D integration for this. You may say, okay, but what about the power CMOS heating in the SFQ? So when you go to cryogenic temperatures, you don't need that high of VDD to drive the CMOS. And second thing is that the energy consumption and hot points just will happen during the writing. So during the reading or the idle, you don't really consume that much power. And since in cryogenic temperatures, you don't have leakage, or your leakage is very, very small compared to higher temperatures. So these SRAMs doesn't need that much bias to keep their states or to avoid leakage or rewrite. So your power consumption at the idle and read reduced by a lot. And the heating doesn't happen that much on the chip. So you can 3D integrate this with SFQ. So this is a sample structure we propose for doing the 3D integration. And you can have these CMOS memories with the interface cells connected to the FPL or SFQ, your SFQ circuits. And the other issue is the speed with the CMOS, since again, in the CMOS, you cannot really go over 2 gigahertz or few gigahertz of speed, and you need to drive your FPL or SFQ at 20 gigahertz. One way is using serialized, deserialized circuits or SerDes circuits that converts this CMOS to SFQ with the correct speed. This is an example of one of the circuits design is RSFQ. It's a little bit large process, but it converts 4 lines to 1 line, so increase the frequency of the from CMOS to SFQ and by 4 times. And this is the measurement results that you can give several inputs like this here, and you can get single line out and convert your CMOS clock to SFQ clock or increase the speed. And we propose also another circuit based on our bistable vortex memory and reduce these large size circuits to these very small circuits, and then convert these parallel inputs to serial SFQ inputs. Yes, is there any questions? Sorry. Okay. So then let's use all these methods that proposed here to do an architecture study and see what happens to our circuit size or the VLSI. So we have this proposed this FFT architecture based on the single pass delay feedback or SDF. Since this SDF method use a smaller amount of memory compared to other methods, so it's more suitable for superconductor integration. And second thing is that fast Fourier transform is data-driven, or it works with the data flow. So it is again suitable for implementing in superconductor circuits which are deeply pipelined, and the throughput can be very high and it can be very efficient for superconductors. For this 1024 basically point FFT, we assume this structure, and for that we need 10 of these BSU unit or butterfly skip units. It's similar to butterfly unit with the skip multiplexer at the output. And in this structure, we try to simulate, basically synthesize these circuits for these different technologies, CMOS, RSFQ, FPL, and FPL plus CMOS memory. For that, we see that our throughput in the FPL or in RSFQ increased by around 15 times, in FPL around by 40x. While you have this many transistors in CMOS, which is the area is very small, since CMOS is very efficient. This is a 12 nano process. But in RSFQ, your area, while getting a good throughput, is around 10 centimeters square, which is not a really practical thing. But if you go to this fast phase logic technology and trying to use the proposed stack, fabrication stack there, you will have a much more manageable 15 millimeter square area there. And with changing the memory from just the SRAM shift register to the RAM with SRAMs in CMOS, you get the same throughput, but at around 50% less area, which is 9 millimeter square, which you can implement easily on a 5 by 5 millimeter chip. And of course, I didn't discuss the power here, but we have a similar power, around 2 or 3 order of magnitude less power consumptions. And in the sport lab, we do other projects and other focuses that I didn't discuss here, which is neural networks, Ising machines, and also focus on quantum computing. So thank you very much for listening and your patience. And this is a picture of our expedition project team at Rochester University in our last group meeting, or in-person group meeting. Thank you.
Thank you very much.